Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over problems 16 to 20 of the June 2019 Algebra 1 New York Regents exam. As indicated in previous episodes, this is a thorough consideration of the problems. If you would like a quick revelation of the solutions, do visit our website at math.serve.com under New York Regents, and you gain access to the transcripts of this video and you can go through it at your desired pace. Alright, let's take a look at question number 16. In question 16, we are going to be assessing our ability to generate exponential models from tables using a TI calculator. We're going to be using the TI 83 Plus calculator. The procedure that we're following is similar to other TI graphing calculators that are permitted on the exam. Question 16 reads, the population of a small town over 4 years is recorded in the chart below, where 2013 is represented by x equals 0. Population is rounded to the nearest person, so we have the years on top and the population at the bottom. The population p of x for the years can be modeled by the function p of x equals a b to the x. This is an exponential growth model, where b is rounded to the nearest thousandth. Which statement about this function are true? Okay, so we have statements about the values of a and statements about the value of b. So what we're going to do is we're going to use this table to generate an exponential growth model, and that model will specify what the a and b values are. So whichever one matches what we get in the calculator here will tell us what the answers are. Okay, so we're going to get started by entering this information into the calculator. Now we want to pay close attention to the information that we're given, so we are entering the correct data values into the calculator. Now one thing you want to note is that we're starting from x equals 0. 2013 is represented by x equals 0. So the year, which we should know, is the independent variable. Okay, so the independent variable is always going to be your x, and this is a dependent variable, the population y, which is p of x. Now 2013 is going to be represented by 0. Okay, and what's the change in the years? The years are going up by 1. Alrighty, so if 2013 is 0, 2014 is going to be 1, 2015 will be 2, and 2016 will be 3. So instead of entering these numbers in the calculator, what we're going to be entering is 0, 1, 2, 3. Alright, so pay close attention to that detail. Now, to enter this into a calculator, what we're going to do is we're going to press the stat button right there. Okay, the stat means statistics. This is a statistics problem using the exponential regression feature. So we press the stat or statistics button. We're going to be entering some data. So edit will give us access to the lists. Okay, so press edit. So we have two fields to enter here. We have the year field and the population field. Okay, so list 1 will be the year. So we're going to enter, well, this information right here. This is L1. Okay, we're going to enter L1, 0, 1, 2, 3, and then L2 will represent our population. So let's go ahead and enter L1 information. We'll start with 0, enter, 1, enter, 2, enter, 3, enter. Okay, so we've populated the first field, which is the year field, 0, 1, 2, 3, representing years. Press your cursor button to the next column, L2, which represents the population. So we're going to enter 3810, which corresponds to 2013 or year 0, 3943, 4081, and 4224. Enter. Okay, so just go over your entry again just to make sure that we didn't make any mistakes entering the data. So 3810, 3943, 4081, 4224, and we have 0123. Perfect. Okay, so now we are going to use the exponential regression feature in the calculator to use this data to create an exponential model. Okay, so what we'll do is we're going to press the statistics button again, and then if you look on the top menu, we have edit, we have calculate, and we have tests. Okay, so we want to carry out a calculation, so highlight calculate, and we have one variable statistic, two variable statistics, linear regression, quadratic regression, cubic, quartic regression. These are all polynomial functions. Keep going down. Linear regression in another format, linear regression. There you go. EXP regression. Option 0 right here is what we are looking for. This is an exponential regression. Okay, how do we know that we're dealing with an exponential regression? You just need to remember that exponential models are of the form that's presented here. Exponential models are of the form y equals ab raised to the x. The independent variable is in the exponential position, which indicates that we are going to be using the exponential regression option. Okay, you're going to see it in a second when we calculate. So we're going to select option 0, press enter. So exponential regression shows up on the home screen. Press enter again. Check this out. You see y equals a times b to the x. That is exactly what we're talking about when we're talking about exponential regression. Notice that this representation matches what we have right here. So we know that what the option that we selected is correct. Okay, so it specifies the a and b values for our exponential model. Let's go ahead and write it down. We're going to round b to the nearest thousandth, and we're going to round a. What did it say to round a to? A is going to be rounded to the nearest ones place, okay, to the ones place, because population, we talk about people here, and fractional persons do not make any sense. Okay, so we're going to round it to the ones place for the a value, and then for the b value, we'll round it to the thousand. Alright, so let me just put it down here. So for the a value, a is 3809.86925, and then b is 1.034984. Alright, so for the a value, we're rendering it to the ones place right here. So break it apart, take a look at the back. Since it's 5 or greater, we're going to add 1. So we're going to round up for this, and then this for the b value, we're rounding to the thousandths place. So this is 10th, 100th, so 10th, 100th, thousandths. Okay, so we're rounding it to this place. Put your line. 9 is 5 or greater, we're going to be rounding up. Alrighty, so our a value to the nearest person or ones place is going to be 3810 because we rounded up, and then our b value to the thousandths place is going to be 1.035 because we rounded up. Okay, so we can clearly see that our answers for question 16 is option 1 for the a value, and this is wrong, and then for the b value is option 4. Bam. Okay, so 1 and 4 are correct. The answer to question number 16 is option number 2. Alrighty, so that is how you use the Texas Instrument Calculator to generate exponential models. Alright, let's take a look at question 17. In this question, we're going to be assessed on how to factor quadratic trinomials. So in this case, we're factoring a quadratic trinomial where a is not equal to 1. So we have 4w squared minus 11w minus 3. and we can see what our A, B, and C values are. So we have A is 4, B is negative 11, C is negative 3. All right, let's write it to the side. A is 4, B is negative 11, and C is negative 3. Alrighty. Now, we're going to use the AC method, or the X game, some people call it the magic square method, to factor this polynomial. Now, since A is not equal to 1, we're going to have to factor by grouping. Had it been that A were 1, it would be easier. We don't have to factor by grouping. We just jump from our completed X game to the factored state. Okay? So we're going to put AC on the top, B on the bottom. AC is 4 times negative 3, which is negative 12. And then B is negative 11. Now we're going to play the X game. Okay? So the question is, what's two numbers multiply to give you negative 12 and add to give you negative 11? So some of you are really smart. You can know exactly what the answer is, but let me go through the whole process with you. Okay, so for 12, we're going to think about all the integers that multiply to yield 12. All the pairs of integers. So 1 times 12 gives you 12. Does 2 go into 12? Yes, 6 times. 2 times 6 gives you 12. Does 3 go into 12? Yes, 3 times 4 gives you 12. We have a complete list of pairs. All right. So which of these yield 11 either by addition or subtraction? 3 and 4 gives you 1 or 7. It doesn't work. 2 and 6 gives you 8 or 4. 1 and 12 gives you 13 or 11. This is what we need right here. 1 and 12. Okay, so we need to pay close attention to the signs to make sure that everything works perfectly. So we're going to put 1 and 12 here. Now the product is negative and the sum is negative. In order for the sum to be negative, either both of them are negative or the bigger is negative. Alrighty? So since we're subtracting here, the bigger one has to have the negative sign. So test it out to make sure. 1 times negative 12 is negative 12, and 1 minus 12 is negative 11. Excellent. So what we're going to do is we're going to replace this middle term with these two values so that we can be able to factor by grouping. So we're going to have 4w squared minus 1. Let's change the color here. Minus 1. Now, minus 1, we're going to add on the variable. So minus 1w, actually it's plus since this is positive, plus 1w minus 12w minus 13. Now, have we changed minus 3? Have we changed the problem? The answer is no. These two are exactly the same thing, okay? Because plus 1 minus 12 is negative 11, all right? All we have just done is we've just rewritten this quadratic trinomial in such a way that we can factor by grouping. Now we have 4 terms. We can group the first 2 together and the last 2 together, okay? Now, what is the GCF that we can factor out from the first 2 terms on the left side of this partition? Well, let's break it down to help you out with it. So 4 times w plus 1 times w. Now, what is common that can be factored out? W is common. Okay, so w is common. So when we are factoring out, it is as though we were dividing by that GCF term that we are factoring out. So when we factor out w, is as though from the first term we're dividing by w, so that's gone, and dividing by w in the second term. So what's left in the parentheses? We're going to be left with 4w plus 1 times 1, which is 1. Okay? Now, we are going to bring down a negative sign. Oh dear. And then on this side right here, we bring down a negative sign. So if we bring down this negative, this is minus. So anytime you bring down a negative sign, guess what happens? You're dividing by negative. So if you bring down a negative sign, this sign right here is going to flip. Okay? So if you bring down a negative and put a parenthesis, well, let's break this down. So if we break this down, 12 is going to be, let's see, we can write this as 3 times 4 times w minus 3 times 1. Okay? So now we're going to factor out negative, negative, factor out the negative. And then we're also, what else is common on the right side of the partition? You notice that 3 is common, so we factor out 3 and a 3 and a negative and a negative. Bring that out. Now, since we factored out negative 3, this minus right here is going to become a positive, all right? So this 3 is divided out, this 3 is divided out. Since we took out this minus, this will become a positive, okay? So you need to keep that in mind. Anytime you factor out a negative, the signs of every term will change. Okay, so what are we left with? We're left with 4w plus, because we took out a minus, 1 times 1 is 1, like that. Alright, this is where you pause and check to make sure your factorization process is correct. How do you know that it's correct? You look at the terms in the parentheses. Are they identical? If they're different, you know you messed up and you have to go back and fix it. If they're the same, which is the case here, you know that everything is great. Alright, so what are we going to do? What we're going to do, we're going to factor out the common factors. These two quantities, 4w plus 1 and 4w plus 1, are common on both sides of our partition. So what does that mean? It means that we can factor it out. Okay? So when we factor it out, we have 4w plus 1. So it's as though these two have been, we divided by 4w plus 1. And then we're going to be left with the terms on the outside, which is w minus 3. Okay? So if we put that together, it's going to be w minus 3. So this is the factored state of the given quadratic trinomial. The answer to question number 17 is option number 3. Alright, so this is how you factor the quadratic trinomials using the AC method. So what do you think about this method? Do you think it's easy, complicated? We know that there are other methods such as the box method, the asterisk method, guess and check. Let us know which method you prefer for factoring quadratic trinomials and why you prefer that method. Just put your comment in the comment section below. Alright, let's take a look at question number 18. In question 18, we are going to be assessed on how to find or verify ordered pair of functions using the calculator again. Okay? Question 18 reads, which ordered pair does not represent a point on the graph? The graph of y equals 3x squared minus x plus 7. Now, how do we know if an ordered pair does not represent a point on the graph? Well, you want to note the following remark, okay? Something that you want to keep in mind about what it means for an ordered pair to be on the graph and what it means to not be on the graph, okay? So an ordered pair does not represent a point on the graph if what? It does not represent a point on the graph if it does not match the input, which is the x, and output, which is the y of x, pairing on the table. From the calculator. Okay, so this problem is pretty straightforward. We're going to enter this quadratic function into our calculators. We're going to then specify these selected input values. Whichever one does not match our output values perfectly are points that are not on the graph. Whichever one matches perfectly are points on the graph. Okay? Alright, let's do it. So we're going to start off by entering the function into our calculator, so you just press the Y button there and enter the function, which is 3x raised to the second power. You can use the square here or caret 2, which is the same thing, minus x plus 7. Enter. All right. Now, if you just press the table value, because we need a tabular of value so that we can know what the input and output values are, if you just press the table, it will give you the default input output value. So let me just fix that. So if we mine was changed, but if you have the default setting, okay, and then you select table, what it's going to do is just going to go 0 and on and on and on. All right. But in this particular problem, we have specific input values that we want to know what the output value is. So rather than the calculator automatically generating input values, we're going to force it to ask us what input values we want to calculate the output for. Okay, so to do that, we're going to press second function window. So that's for table setup, second function window. Okay, so we're going to tell it to ask us what the independent input, ask us what the input values are, so that we can know what we can focus our attention on the desired output values. Okay, all right, so what are the input values that we're going to be entering? Let's make a table real quick. All right, so the input values are our x's. All right, input values are going to be our x's, and then our output values are the y's. And then we have the ordered pair. So the input values that we're going to look at are negative 1.5, and then the next one is 0.5, and then the next one is what? 1.25 and 2.5. Okay, so let's put these input values in our calculators. We're going to look at the output values and look for the one that does not match what we get from the calculator. Okay, so now we're going to go to table. Second function graph takes us to table, and notice it's blank. So we have to enter the input values. Nice. So negative 1.5 is the first one. Press enter. It generates the output value. 0.5. Enter. Generates the output value. 1.25. Enter. Generates the output value. And then 2.5. Enter. Generates the output value. Okay, so these are our output values. Okay, so let's put it in. So our output values are, what are they? 15.25. And the next output value is 7.25. The next output value is 10.44. And then the last one is 23.25. Okay, so what we're going to do is we're going to compare, okay? Which one does not match these pairs perfectly? So 1.5, 15.25, check. This one matches. Okay, so this is good. Don't have to put a check mark here. And then the next one is 0.5, 7.25, check. It matches this perfectly. Next one is 1.25, 10.25. Ladies and gentlemen, we have a problem. This does not match. Does not match. Okay? So this is the point that's on the graph, 1.25, 10.44. But this is 10.25. This is not going to be on the graph, all right? This point is going to be lower than this desired point. The other one is 2.5, 23.25. That's a check also. So ladies and gentlemen, we can clearly see that the answer to question number 18 is option number 3. So this is how you can find the ordered pair of functions desired output values using the TI-83 calculator. Alright, let's take a look at question number 19. In question 19, we're being assessed on how to identify arithmetic sequences when a data set is presented in a list form. So number 19 reads, given the following three sequences, so we have three sequences here, which ones are arithmetic sequences? So in order for us to identify an arithmetic sequence, we need to know what an arithmetic sequence is. We need to know how the terms of arithmetic sequences are generated. So we need to refresh our memory real quick. So you need to recall that terms of arithmetic sequences are generated how? Are generated by adding a constant term that's known as the common difference, by adding a constant term every time. So repeated addition, just like linear functions, is a process that generates arithmetic sequences. Okay, so which of these exhibits that pattern of repeated addition? That's the goal. Let's start with option 1. Option 1 is 2, 4, 6, 8, 10. Dot, dot, dot. So is this repeated addition of the same number every single time? So from 2 to 4, that's addition of plus 2. From 4 to 6, plus 2. From 6 to 8, plus 2. From 8 to 10, plus 2. So what's happening here? We're adding 2 every time. We add a constant. We add the constant 2 every time. So what does that tell us? It tells us that this, ladies and gentlemen, is an arithmetic sequence because you're adding the same number every single time. Alrighty? Now so this one is good. It passes the test. This is an arithmetic sequence. Now let's take a look at the next one. Option 2. We have 2, 4, 8, 16, 32. Alright, so what's the deal here? From 2 to 4, you add 2. From 4 to 8, you add 4. From 8 to 16, you add 8. From 16 to 32, you add 16. Ladies and gentlemen, is this an arithmetic sequence? Absolutely not. Why not? Because in this scenario, you're adding different numbers every time. Okay, so when you add different numbers every time, that tells us that it is not an arithmetic sequence. So what kind of sequence is this? If you look at this pattern closely, what you notice is that you're actually multiplying by the constant 2 every time. Do you know what kind of sequence that is? It's a geometric sequence. When you multiply by a constant every time, that is a geometric sequence. Alright, so number 2 is no go. Number 2 is geometric, it's not arithmetic. Okay, let's look at the third one. Option 3. What's going on here? We have a plus 2, a plus 4, a plus 6. What on earth is this? This looks really weird. Okay, let's see. We're dealing with algebraic expressions. From a to a plus 2, what do you do? Plus 2, you add 2. From a plus 2 to a plus 4, this 2 has grown by a value of 2, so we add 2. Yeah? From a plus 4 to a plus 6, what do? You add 2, because 4 plus 2 is 6. From a plus 6 to a plus 8, what do? You add 2, because 6 plus 2 is 8. Ladies and gentlemen, we are adding 2 every time. So we add the constant 2 every time. So if we're adding the constant 2 every time, what does that tell us? It tells us that this is an arithmetic sequence of an algebraic nature. Even though it looks weird, it is an arithmetic sequence too, okay, because you're adding a constant every single time. So out of these 3, options 1 and 3 are arithmetic sequences. So the answer to question number 19 is option number 2. Alright, let's take a look at question 20. In question 20, we're going to be assessing how to identify integers and rationals for domains. Question 20 reads, a grocery store sells packages of beef. The function C of W represents the cost in dollars of a package of beef weighing W pounds. The most appropriate domain for this function would be, so what's the most appropriate domain? So we need to identify what the domain is. The domain is the inputs. Okay, so remember that domain is the inputs. Okay, so W is the domain and it is the input. The input is the weight in pounds. Okay, so how can you represent weight? So something to keep in mind is what happens when you step on the scale. When you step on the scale, what type of numbers do you see? The weight of an object, can be represented by whole numbers. So you can be like 150 pounds by whole numbers and fractions also. Okay, so it could be 150.5 pounds. On a scale, it's going to show 150.5 if it's a digital scale. But if it's an analog scale, you just follow the tick marks for the fractional weights. Okay, so this is basically the set of integers plus fractions. So integers plus fractions represent rationals, but they have to be positive. Okay, positive integers and positive fractions. Why is that? Can you have a negative weight? That doesn't make any sense, right? Your weight has to be positive. There's no way that you step on a weight and it dials backwards or shows you negative. Okay, so a combination of positive integers and positive fractions gives you positive rationals, and that's what does a reasonable representation for the domain. Okay, so the function C of W, we're focusing on the domain, which is the input. Okay, the domain is the input. The domain, ladies and gentlemen, is the weight. So the domain is W, and the appropriate representation for weight is positive rational numbers. Alrighty, so let's look at the options that we have. Integers are just positive and negative whole numbers. This fails because you cannot have a negative whole number as your weight. So option 1 is wrong. Option 2, rational numbers are positive and negative whole numbers and fractions. This does not work because you cannot have a negative whole number or a negative fraction as a weight. Positive integers, these just represent positive whole numbers. Is everybody's weight a whole number? The answer is no. In most cases, your weight is hardly ever a whole number. Sometimes it is. So positive integers is not complete, is missing the fractional component. Now, positive rational numbers, a combination of positive whole numbers and fractions, is perfect, because even if your weight is a whole number or a fraction, it can still be captured by this domain set right here. So the answer to question 20 is option number 4. Thanks so much for taking the time to watch this presentation. We'd like to know what you think about this tutorial. If you found the contents of this presentation helpful in your preparation for the upcoming Regents exam, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions, comments, requests, or suggestions, just post it in the comment section below and we'll be more than glad to respond. Don't forget to subscribe to our channel for updates to the remainder of this review series. More great support resources can be found at our website, math.serve.com. Do check it out. Thanks again for watching and have a wonderful day. Goodbye.